Okay, so this is chapter 1 in biology class, Bio 3. You guys should have your outline with you as you're going through these PowerPoint slides in the lecture because I refer to them and you can take additional notes. So you'll have chapter 1 in front of you, and the first part in chapter 1 talks about biology and what is biology. So biology is the study of life. And the word biology, right? Bio means life. Like if you wrote a biography, that's the story of your life. And the study of is ology. So biology, the study of all life. And biology is a science, which is an approach to understanding the natural world around us that's based on inquiry and a search for information, right? So let's talk about science real quick. So science, there's two different ways to approach science or how science is done. So one's called discovery science, and the other one is called the scientific method or a hypothesis-based science. So in your outline, I have it in outline form. So Roman numeral 1, those are the Roman numerals are the big topics, and then it's subdivided with A, B, C, D underneath it, and then those A, B, C, Ds are further subdivided. So if you look at Roman numeral 2, the process of science, in your outline, you can see there's an A and a B. So A is discovery science, and B is the scientific method. And then underneath each of those topics, we have subtopics. So underneath discovery science, right, so we can see from the PowerPoint slide, what discovery science is involves collecting data through verifiable observations and descriptions, and then you base your sort of conclusion on inductive reasoning, so some kind of inductive logic. The important thing here is to realize that you have verifiable observations and descriptions. So other people can come to the same conclusions that you can. So you can't say like the flower is pretty because somebody else might not think it's pretty, but you can say the flower has 6 petals, right? And anybody can come along and say it has 6 petals. So 6 petals is sort of the verifiable observation. Like anybody can come along, come up with the same observation as you. So in your outline, you have large amounts of data with the goal of finding new patterns or correlations. The data largely depends on observations, and I go on to say in your outline they're verifiable. Number 3, the process is known as inductive reasoning. So when you have a lot of data and you're looking at all your data, all of your observations, you can come up with a general conclusion or a generalization of all that data. So we'll go through a few examples here in discovery science. So the first one that's kind of more computer-based is data mining. So what these companies will do is they will gather an extraordinary amount of data on people, right? So your activity on the internet and on your credit cards and your ATM cards, that all can be gathered. So what you buy, what you look at, what you like on social media, the news articles you click on, just like all of that data goes into one big pile, right? And someone can come along and look at all of this data and make certain conclusions about you. And so they induce that perhaps you are, female or male. They induce that you are, your political leanings, if you're more conservative Republican or if you're a liberal Democrat. They can, come up with lots of different things about you. And then what they use that data for is to, in terms of like, our social media or our, Amazons of the world, they want to sell you things, right? So they're going to target advertisements at you, but they want to make sure that these advertisements are a waste of their time. So they're going to make inductive reasoning. They're going to induce that you probably will like, you know, vintage clothing other than, rather than like J. Crew. So they'll put more vintage clothing in your feed. So that's kind of an idea of data mining. So you have a whole lot of information on something, and you come to sort of a general conclusion based on all that data, right? You're not coming to and you're basing your general conclusion on inductive reasoning, right? So that's one example. The other example is more biology based. So this is Schleiden and Schwann's cell theory. So these two guys when the microscope was just being invented, they used it to look at all different kinds of living things, and they took very, very careful notes and drawings. So this is an example of some of their drawings that they made of all the different kinds of organisms and plants, fungi, molds, different things that they put into the microscope, and they came up with this everything basically was made of these little units, these little, so you can see these units here, these circles, these squares and rectangles, and said everything living is made up of these little units, and we're going to call them a cell. So cells, the word cell was actually used for kind of a dorm room that the monks used to occupy. They called them cells. And so they used that because they look like little quarters, little rooms, right? So that they looked at all these different living things. Everything had cells. And so they, basically came up with this inductive reasoning that all living things are made of cells. And that's the cell theory today. There's a little bit more components of the cell theory, a few more components, but in terms of discovery science, right, they just had a lot of observations. They had a lot of verifiable, reproduced observations. Anybody can look at these things under the microscope. Anybody can see that they have these units, and they came up with that, the cell theory. My last example here is Darwin. Darwin's travels to the Galapagos Islands. In particular, he took very careful notes of all the organisms that lived on the different islands, and he came to the conclusion that based on their body shapes and sizes, he saw that there was a relationship between the different birds and the different iguanas on the islands and on the mainland, and that they're similar enough but then diverged in small ways to make them better fit for their island and for their specific environment. So from his notes and from his large mass of data, he induced that that there was probably a common ancestor or some kind of organism that when it went to different islands, it changed over time in small ways to make it better fit for that environment. And so that ultimately becomes the theory of evolution and natural selection. Okay, so those are some discovery science. That's basically discovery science. I hope you understand that concept. And now there's another way of doing science, which is this hypothesis-based science. So this is, you're going to have to know for the exam the steps of this scientific method. So if you look at your outline, steps 1 is observations, 2 is a question, 3 hypothesis, 4, 5. 5 is the experiment. And if you turn the page all the way down, there's number 6, there's the data. Number 7, analysis, conclusion. And then that's it, analysis and conclusion. All right, so let's look at the first step is an observation. So when you do science, right, again, we have to deal with the real world, and we need to observe things happening in the real world. So this really easy example is a flashlight not working. So another thing about hypothesis-driven science or hypothesis-based science is that you do it every single day. You just maybe you don't know you're doing it. But this example will show you how you're doing science every day. So you find that there's something in the real world that's a problem. The flashlight's not working. And then you always ask yourself, right, well, what's the problem? What's wrong with the flashlight? So that's your question. And then you form a hypothesis. And all a hypothesis is a guessed answer, right? So in your notes, I have a different example. I have pie crusts, right? So your observation in life is that pie crusts are flakier. Some pie crusts are flakier than others. And then your question is, well, what ingredient in pie crust can cause the difference in flakiness? And then your hypothesis is just your attempt to answer that question, right? So in your battery example, if your flashlight's not working, then you usually just go ahead and change the batteries, right? You just assume that's the batteries that are dead, but that's your guess. You think that the batteries are dead. The hypothesis is the batteries are dead. The thing with the hypothesis, though, it has to be testable, okay? So you have to be able to test your hypothesis in order for that hypothesis to be a real workable hypothesis. You could hypothesize that the flashlight's not working because somebody put a spell on you, or that, aliens came down and they zapped anything that uses batteries in your house. Those are also guessed answers as to why your battery's not working, but they're not grounded in something that can be tested, right? So we need to be able to test using the real world and using real physical objects and physics and the laws of physics that exist to test your hypothesis. So your hypothesis is the batteries are dead here. Then what do you predict, right? So the prediction is if you go through your testing the hypothesis, you should be able to know what the outcome would be. So you predict if, and the prediction is always in this if then statement. If the batteries are dead and you replace them with new ones, then the flashlight will work, right? So this is a nice prediction. Based on your prediction, you can create an experiment or a test, right? So you're going to replace them, replace the batteries. Now, two scenarios can happen because this is your experiment, right? You don't know what's actually going to happen, but you're going to replace the batteries and the batteries don't work. So the flashlight still does not work. So your test, and I shouldn't say test, it should be the data, right? The data here is that you turn on the flashlight and it turns on or it doesn't turn on. So your data says, oh, doesn't turn on. So does your data support your hypothesis? Is your hypothesis correct that the batteries were the problem? No, right? Because you changed the batteries. And so the flashlight didn't turn on. So your hypothesis is not correct. So what do you do in this scenario, right? If the batteries are not correct, what do you go back and change? Do you change your observation? No, because that's the same. The flashlight still doesn't work. Do you change your question? No, because you want to still know what's wrong with the flashlight. Aha, you change your hypothesis, right? So the arrow points to hypothesis, you need to change that. So you might just say like, some kind of internal structure is damaged, okay? So then you would go ahead and create another hypothesis. So you would say like, the on-off switch is not working. Okay, so then you need to make a prediction. If I fix the on-off switch, then the flashlight would work. Then you do that test. So that's how you would deal with a data that does not support your hypothesis. The alternate route is easier, right? So if your flashlight turned on because you changed the batteries, then your test or the data that you got from your test supports your hypothesis. The evidence here shows you that it was the batteries, right? So your prediction is correct and you're on your merry way because you have a fixed flashlight. Okay, in the outline, we kind of use the pie crust scenario here. The pie looks delicious. So the question is, or the observation is, hey, I've had lots of pie. Some crusts are flakier than others. Your question is, well, what ingredient used in the pie crust recipe can cause a flakiness, and what's your hypothesis, right? So you would think about what's in pie crust recipe, and you say, oh, I think it's the fat, right? The fat used in pie crust recipes contribute to the flakiness. And then you make a prediction. If I make two pies using different fats, then I can taste the crusts and see if one is flakier. And then the experiment is easy now because you know already based on from your prediction like what you're going to do. So you're going to make a couple pies, you make one with lard, you make one with butter, and then what's your data? The data is eating them, and then you gather which one's flakier, right? So then you can look at that, and if they are the same flakiness, right, then what do you do? They go back to your hypothesis. You're like, oh, maybe it's not the fat, maybe it's the amount of flour, or maybe it's the salt, so you can go back and change that. So you're doing hypothesis-based science every day. So here's a little scenario that I usually do in class, right? So here's an observation. So we were just going to fill these out, right, based on this little picture here. So the observation, your car broke down, right? Car's not working. What's your question, right? It would be, why is my car not starting? And then the hypothesis, your best guess at answering your question. Why is my car not starting? Maybe it's out of gas. Okay, so you make a prediction. If I fill the tank of gas, then the car should start. You test it up, you put some gas into it. Your results, you turn the key and it still does not turn on, right? You gassed it up, but it's still not working. So what's your conclusion? Your conclusion is it's not the gas, right? So then you go back and you change your hypothesis. You want to change that and you start all over again with your test and your results and your conclusion. So that's basically your scientific method, and you do it every day probably, right? All right. So let's see if we can answer this question. Which of the following best describes the logic of the scientific method? So I'll give you a second to read it. So what I do with these questions is in class, I would usually just have you guys read them and you would just say the answer. In the online classes, I'll just say pause it, think about it, come up with your own answer, and then I'll just tell you the answer. So go ahead and pause it here if you want to think about it. All right, so if you thought about it, the answer is letter D. D as in dog. If your hypothesis is correct, I can expect certain test results. Yes, because you're going to predict, right? If then, if my hypothesis is correct, then this is what I should see. All the other ones are problematic. If I generate a testable hypothesis, tests and observations will support it. No, your test doesn't have to support, like, really it's the data that would support it. Observations don't support it. So this is a kind of a weird, incorrect statement. Letter B, if my prediction is correct, it will lead to a testable hypothesis. That's opposite. Your hypothesis happens first. If my observations are accurate, they will support my hypothesis. No, right? Your observations, going back to the flashlight, the flashlight didn't work. How does that support your hypothesis that the batteries are the problem, right? This is a weird statement also. So D is the only one that makes logical sense. All right, so let's see if we can develop a hypothesis. A day after a picnic, you look into a cooler with melted ice. Only 2 cans of soda are left. Diet soda that's floating and the regular soda that's at the bottom. You pick up the cans and see that they are the same soda, only one is diet. So here are the ingredients. The regular soda is at the bottom, the diet soda is floating. Write down at least 2 possibilities that explain why one floats and the other didn't. All right, so write a hypothesis explaining why one floated and the other sank. Is this hypothesis testable? How would you test it? What equipment would you need? So these are things that a scientist, right, or someone who really wants to get down to the real answer to a problem would ask themselves. So I'll just pose one. Maybe you have something else in mind. But we can see from the ingredient list that all the ingredients are the same except for one, right? So there's sucrose here. Sucrose is table sugar. It's real sugar. Aspartame is a sugar substitute. So they're different molecules, different substances. So my hypothesis would be that the sucrose weighs more than aspartame because this one sunk the soda at the bottom where aspartame is floating. So then what would be my hypothesis, right? My hypothesis is that sucrose is heavier than aspartame. And is this testable? Absolutely, because I can get my hands on some table sugar. I can get my hands on some aspartame. These are just little packets you can find at the coffee shop. And you can weigh each, like the same amount of each, and you can see if they actually, if your hypothesis is correct, if sugar actually weighs more than the equal amount of aspartame. What equipment would I need? I would need a scale, and I would need some sucrose, and I would need some aspartame, right? And I would also want to have the units the same. So I want a gram of sucrose and a gram of aspartame, right? You can't just rely on those packets. Those packets can have different amounts. So I'd have to have some kind of equipment to make sure that there's an equal amount of each. It's like a tablespoon, maybe a tablespoon of sugar and a tablespoon of aspartame. All right, let's move on. So let's talk about variables. So now we talked about sort of the flow of the scientific method. Let's look at variables. So if you turn the page under number 5, the experiment, when you do science experiments, you are working with variables. One variable is called the independent variable and the other variable is called the dependent variable. So I'm going to talk about the independent variable. So the independent variable is what you would change in the experiment. So in this example here, we are working with some kind of new fertilizer, fertilizer X. And you want to find out if the fertilizer X makes a big difference in plant growth, right? So your independent variable, the variable that you're changing, is the type of fertilizer. Let's say you use no fertilizer on one plant and your fertilizer X on the other plant. What is your dependent variable? What the dependent variable is, it depends on your independent. So this is the plant growth, or things that are observable, right? So the number of leaves that you get on the plant, or maybe even the number of fruits that you get on the plant. So this dependent variable is affected by the independent variable, right? So when you are doing an experiment, you have an independent variable that you're working with, and then your data is going to show you the dependent variable. It's the response or the effect under investigation. Okay. So when you create an experiment, let's talk about this as another example of independent and dependent variables. So the experiment is, are test scores impacted by the amount of time spent sleeping the night before? This is probably, I don't know, hopefully you guys get a good amount of sleep the night before you take a test, but I think that most college students don't. So what would be the independent variable here? What are you working with, right? What's changing the scientists can manipulate? It would be probably the time of sleep, right? What's the dependent variable here? The dependent variable is the score on the test, right? So does the amount of sleep, does the independent variable cause a difference in the dependent variable, the score? So that is an example of an independent variable. Okay. So moving on to creating the experiment. So a good experiment will have a control group and will have an experimental group. A control group is a group of people, or it can be a group of plants, or whatever you're working with. You have a set of the experiment that you're not using the independent variable on. You're not using anything different. You're kind of just letting it go naturally. And then in another group, the experimental group, you're actually using your independent variable. You're manipulating the scenario to see if something, your independent variable is having an effect, right? Because you need your control group to see whether the experiment is changing what would normally happen. So in this example, we have the experiment is, will student test scores be affected by distracting sounds in the testing environment, right? So what's your independent variable here? It's going to be your distracting sounds, right? So your control group is going to take the test normally under normal situations, which is quiet. And your experimental group is a set of students that are taking it with that distracting noise, with the independent variable. So what's the dependent variable here? The dependent variable is going to be their test scores, right? So now I can look at, well, if the test scores are the same between the two groups, then your conclusion would be that no, right? The distracting sounds did not affect their test scores. But if the test scores are drastically different and, hey, maybe they're better or maybe they're a lot worse, but that would be a dependent variable and that would be your data. And so you can draw conclusions based on that data. All right. So in your notes, right, we have letter C, creating the experiment. We have the experimental group and we have control groups. Now we can go on a little further in your outline and say there's a positive control and a negative control. So I don't have a slide on that actually, but a positive control group is a control group would have known positive results. So we know that if you can concentrate in a quiet room, that that you're probably going to do better on the test, right? Let's just use this example. So that would be a positive control. A negative control would be something where you would know there's no way this, you're going to get a positive outcome. So you set up a scenario where you're you are just creating something where you know it's not going to be a positive outcome. So in this negative control, maybe you have people, taking a test, but then interrupted every 2 minutes and ask questions and not given enough time to take the test. Just very, very distracting, so they cannot get a good grade. And then you want to see if your experiment of just music would be distracting. Okay. So you have these positive controls and negative controls so that you know exactly what's the best score these kids could get when it's quiet. All right, maybe it's 90%. And then what's the worst score they could get if they're just constantly distracted and you're poking them and playing loud music and asking them questions and et cetera, et cetera. So maybe the worst score they get is like a 45. So then you know your parameters. You're like, okay, the best they can do is 90. The worst they can do is 45. What does music do, right? So then when music plays in the background, maybe they get an average of 60. Okay, so then you kind of understand how the music affects them with the best and worst case scenario. Okay, so I hope you understand that. So good experiments will always have a positive control, negative control, and then your experiment. Okay, so let's move on. In this area where you have control groups, sometimes if you're working with people, let's say, you will have a placebo being used. So if you look at the word placebo, many negative control experiments will use a placebo. And this is usually, or most of the time, used in testing out new medicines or new treatments for people for health purposes. So a placebo is a known negative. So it's a medically ineffective treatment used in a control group. And it's so that you can treat the two groups the same. Because in a good experiment, you want all the subjects to be treated the same. You don't want anything to change except for that one independent variable that you're testing. So the placebo effect, however, the placebo effect is very real. I do have a placebo effect. So let's move on to my example here. Let's say you're testing out a new sleeping pill. How would you know that the sleeping pill worked? So for example, you have 20 people that have insomnia, and you want to see if a new herbal supplement can make them go to sleep. Design an experiment to try and find out your herbal supplement, to try and find out about your herbal supplement. Okay, so what could be the experiment test? What could be the positive control? And what could be a negative control? So you know that if these people can't sleep, you could give them the positive control would basically just leave them alone, right? So we know they're not going to sleep because they have insomnia. So the positive control group would be like, okay, you guys just go to sleep and nothing happens to them. The negative control would be the placebo. So you can give them, instead of giving them the drug, you give them placebo. So the placebo looks like a drug. It comes in a pill, but inside there's no active ingredients. It's just sugar or it's just something inert. So they take the pill, but you know that they should have no benefit from this because it's not active. So that's your negative control. And then your experiment would be your herbal supplement, right? So then you have your positive control would be people without anything. Your negative control would be people with this placebo. And then your experiment would be the herbal supplement. But why would you do the negative control? Why would you have that placebo? Well, there is something called the placebo effect. And if you go up a little bit higher, so some people, just based on the fact that you're taking something before bed, it makes their brain think that they should be able to fall asleep quickly, and sometimes that works. So the placebo effect is a real effect that works. It makes people really their symptoms of disease or anxiety or different things like that actually do quiet down from the placebo effect. Let me see if I have another example of placebo effect. No, okay, sorry. So anyhow, the placebo effect is very strong. So if you want to know that your drug actually worked based on, you have to compare it to placebo. So if half of the subjects fell asleep better on the placebo and half of your subjects fell asleep better after taking your herbal supplement, Well, then does your herbal supplement work? No, because it's the same as taking nothing, right? So you really want to look at when drugs are being made and when experiments are being done, they always put a placebo in to make sure that the placebo effect is not the driving force behind what's working, that the actual drug, whatever the herb is or whatever the drug is, that that molecule is actually creating a significant effect. Okay, so that is that. So when you create an experiment, you have, just to go over this this part once again, when you create your experiment, you always have an experimental group and control groups. Control groups can be positive control and negative control. In negative control groups, a lot of times they use a placebo just to make sure that the placebo effect is not what's driving the effect of an experiment. Okay, so the drug actually has some worth if it has different outcomes than placebo. Hopefully that makes sense to you. All right, let's move on to our last topics here, single blind and double blind experiments. Okay, so single blind and double blind. A single blind study, and this is again based on human participants. A single blind study is that the patients don't know whether they are taking the treatment or placebo, and they control the dosage forms. There's a control in the dosage form. So the patients don't know, but the doctor does, or the experimenter does, right? So the experimenter, the scientist, will give one group placebo, one group the medicine, and they are aware of who's getting what. However, in a double blind, both the patient and the doctor are in the dark. So there's a third party that has the information, but the third party is not telling the person that administers the test. They're not telling the patients that are receiving the test. And this is the gold standard for new medicines. It's the double blind, because if neither person, the doctor nor the patients, know who's getting what, then nobody has expectations, right? A lot of times even like the doctors or the people that are performing the tests, they already have, or they want, or, there's some kind of feeling that they're going to be looking for small changes, maybe more acutely in the people that are getting the drug versus the placebo. So there might be a bias on the doctor's side just to look for small changes that they may not have seen if they didn't know who was getting what. And then on the taker's side, on the patient's side, if they knew they were getting the placebo, or if they knew they were getting the drug, they might actually start to feel better. It's like the placebo effect all over again, right? They would actually feel certain ways, or if they know what the doctors are looking for, they might actually start to express those results, even just subconsciously. So the double blind is really best because the patients have no idea. Sometimes they don't know. Sometimes the doctors will say, "Oh, it's for this," but it's a little bit different. So anyways, the double blind is the best because there's no bias that can be introduced. All right, so in your notes, single blind experiments keep some information away from the investigator or participants so they can be unbiased and fair. Double blind is the gold standard. Neither the researchers nor the participants know if they're experiment or the control, and it prevents any bias on both ends. So rationale for single blind studies, right? Sometimes participants try to guess at what the experiment is trying to show and alter their behavior to conform to what they think the researchers expect. Imagine that the researchers are doing a study to determine if a certain type of medication causes people to feel more alert. If they knew that we're testing a hypothesis on increased alertness, they might start acting more alert after ingesting the medication. So even if the medication is not working, this is placebo, right? They might just like make themselves, like they psych themselves into thinking that they're more alert because that's what they think that the researchers want, right? So if you use a single blind procedure and not tell the participants what they're looking for, the people in the study are less likely to have inadvertently biased the results. And so the double blind is even better than that because again, the researchers themselves can start to have bias. They can start to look for differences in the patients because they know who got placebo, who got experiment. All right, I know I'm repeating myself, but the double blind is the best. Okay, so let's wrap up. So the data, number 6, is the measurement and observations of your experiment. So from the pie crust example, it's the taste of the pie crust. What would be the data from your sleep experiment? So going back to the sleep experiment, right? What's the data? Well, it'd basically be like how many hours of sleep the patients got, or maybe they can report on how quickly they fell asleep, or how the quality of their sleep, which is again a questionnaire you'd have to ask the patients, right? How would you rate your night's sleep? Good, bad, whatever. And then the conclusion, right? You look at the data, right? The conclusions are based on data. So you look at the data, and then you have to reach this logical conclusion. A lot of the problems in sort of like outside of science, or even within the science community, is like sometimes the data can be fuzzy, or the data can be interpreted different ways, and so you can do more experiments to clarify the data, but your data is really what you want to base your results on. So something like climate change, where there's just so much data out there that tells all the scientists that are looking at this data have to conclude that the climate is drastically changing. It's changing because of man's activity, right? Human activity. And there's no refuting that data. But then some people will refuse to look at the data, and they draw their own conclusions, not really looking at the data. It's a belief system. So that's what's really frustrating sometimes, is that the the average person out there may not look at the data, or have access to the data, or not understand the data, and so they rely on the scientists to look at it. And sometimes if you don't like that data, if you don't like the news, you'll invent a different narrative, and that's kind of dangerous. So we always want to look at the data and make judgments based on the data, right? So right now we're living through a pandemic. There's a virus out there, and we're gathering data on how the virus replicates and how the virus is passed from person to person, and how we can prevent that. And we need to look at the data for that. And we can't just invent our own truth because we have to look at what's actually happening, and that's what the data is for. All right, so I'm going to pause it. We'll do part 2 of chapter 1 in the next video.